Hello, it's Muhammad Ragab, a PhD student at the Data Systems Group, Tartu University, Estonia. In this video, I'm going to present a small presentation of my accepted PhD symposium in the DOLAP 2020 workshop at EDBT ICDT conference with the title Querying and Processing Big Property Graphs. As you might know, we have two main categories of graph processing, graph queries and graph analytics. The graph queries can be with the pattern matching or in the form of path or navigational queries, while the graph analytics are the algorithms that we can apply or compute over these graphs. In this paper, we are interested in the graph querying category. We have different graph query workloads. Actually, the local OLTP graph queries as simple computations in a small set of data, and the global OLAP graph queries with complex aggregations that touches significant portion of the data. Indeed, we will have scalability issues with the rapidly increasing graph datasets in both size and complexity. Graph query evaluation mainly depend on the graph scope, which means the number of nodes and the edges it will touch while evaluating the query. Therefore, it might take unexpected times, especially with the complex OLAP query workloads. Thus, distributed graph query evaluation is kind of solution to tackle such scalability issues. In fact, we have plenty of graph databases, such as the most popular graph database management system, the Neo4j. However, the problem is Neo4j and most of the current graph databases are optimized for the OLTP graph query workloads and OLTP operations only and for the subgraph traversals, and most of them are centralized solutions that can't handle large graphs with complex OLAP queries, but they are not optimized to handle the large and complex graph computations or OLAP queries. And recently, Neo4j has developed a promising framework called Morpheus or Cypher for Apache Spark, which aims to extend the Apache Spark defacto distributed large data processing framework with the capabilities of graph query language, Cypher. Actually, Cypher is an industry most widely used property graph query language defined and maintained by the Open Cypher community. This system aims to incorporate the benefits of Cypher graph query language from the graph database domain into the world of the distributed Spark data flow processing. Specifically, it is built on top of Spark SQL and it can be integrated into the Spark Analytics program. So, the vision of Morpheus is to bring the graph capabilities to the data integration and analytics world, the OLAP world, I mean. So, actually, Morpheus can currently provide some powerful features such as distributed Cypher graph queries, which comes with enabling the OLAP style graph query workloads using Spark pipeline, and Morpheus also enables integrating different graph and non-graph data sources from multiple storage backends. In the context of Morpheus, they call these sources as PGDs or property graph data sources to be represented as one or multiple graphs in Morpheus. Last but not least, being built on top of Spark enables Morpheus to integrate with other Spark libraries and packages such as Spark MLib for machine learning tasks and GraphX for graph processing and graph structured streaming, Spark structured streaming. However, Morpheus still has some limitations. For example, it currently supports the property graph data model, but it's not directed to deal with any variants of these property graphs, such as the path property graphs. It is also not supporting the RDF popular graph data model. Morpheus doesn't yet support regular path queries, and it also cannot handle two complex graph algorithms, such as the algorithms that will be translated into recursive SQL queries. This is a problem related to graph to relational challenges. Now I will talk briefly about our proposed contributions that I'm planning to do in my PhD. First of all, we aim to assist Morpheus project in two folds: the storage data source benchmarking. In this point, as we have mentioned, Morpheus can read and write different its property graphs from different PGDs, different property graph data sources such as the HDFS, Hive, and in different file formats such as CSV, Parquet, and ORC. And because large graphs do require well-suited persistence solutions that are efficient for query evaluation and processing, we aim to provide a comprehensive storage benchmarking on these BGDs for Morpheus to discover the best performing ones to store the graph data in. And we also aim to provide some graph-aware query optimizations or optimization techniques. In particular, we aim to use some strategies to optimize graph query evaluation in the pure relational Morpheus. I will explain this more as Morpheus is built on top of Spark SQL, as we have mentioned. Therefore, at some point, the property graph data and the graph schema are translated to relational world of Spark data frames and tabular schema. Cypher graph query also are translated into pure relational operators that will work on top of these data frames or tabular data. And these queries will also be optimized with the pure relational Catalyst optimizer for the Spark SQL. And therefore, Morpheus is a pure relational context, as you can see. Therefore, applying some graph-aware optimizations in Morpheus will enable great improvement in processing the large property graph datasets within it. We propose to provide some graph indexes on the efficient discovered storage backends. We will discover these from the previous contribution, as we have mentioned, and then we can propose some graph indexing on those storage backends. We also think of providing some graph materialized views to efficiently help in the query evaluation. We can make materializing of the intermediate results in these graphs. We think also to extend the Catalyst query optimizer of Spark SQL to be graph aware, providing some graph aware cost-based optimizations to it. Last but not least, we propose to use graph partitioning techniques to organize the property graph data and improve the query performance. We really believe that achieving these contributions can significantly enhance the performance of executing graph queries on top of the Apache Spark, and specifically the Spark SQL library. In this paper, we applied first phase of this of the benchmarking, of the storage benchmarking. As you might know, we have different graph benchmarks with various workloads. For example, the local OLTP graph query workload, we can have the LDBC SNEP interactive benchmark, and for the global OLAP graph query workload, we can have the LDBC SNEP business intelligence benchmark and the train benchmark. And for the graph analytics workload, which aims to apply the graph computations or the graph algorithms, different graph algorithms, we can have the LDBC graph analytics benchmark. In our initial experiments, we apply some initial benchmarking queries for evaluating the performance of Morpheus on top of different storage backends such as Neo4j, Hive, and HDFS. And for the HDFS, we have different file formats such as CSV, Parquet, ORC. We have used the LDBC SNP Business Intelligence Benchmark workload with 18 atomic or micro benchmarking queries and 21 queries of the business intelligence queries. And the initial results can be found in our CAPS repo. To this end, I'm finishing my presentation, and you can, if you have any other questions, you can like post email to me, or any questions can be are more than welcome. And thank you very much.